So in the last class, we were doing cup calorimeter, bomb calorimeter. So just for a review, what are the equations you are using for cup calorimeter? What are the equation we were using? Yes. Q equals to MC delta T. Yes. This is the equation we were using for cup calorimeter. And what was the equation for bomb calorimeter? Bomb calorimeter, Q equals to? Yes. Yes, C delta T. What is the unit of this C? This is heat capacity, right? What is the unit? Yes, through. Very good. And what is the unit for this C? Joules. Yeah, this one. Specific heat capacity per gram per degree Celsius. So heat capacity is of the bomb calorimeter. And what was the equation we were using for delta H? Delta H. The equation for delta H. From this Q. How this Q and delta H are related? Q is in kilojoules or joules, right? But delta H is in kilojoules per mole. So Dhruv is again right. To calculate delta H naught, we are going to use, is it Q of water or Q of the reaction? If you take Q of the reaction, then it will be like this. But in the cup calorimeter and bomb calorimeter, you are calculating Q of the water, right? That is the surrounding. So what's the equation, Lasya? Yes, very good, Dhruv. Q of the water over N. Remember that. If you take this, but you're not calculating this. What are you calculating? This. Your thermometer in cup calorimeter, bomb calorimeter is dipped in water. And what is water? Water is the surrounding. See here. Thermometer is dipped in water. Now we are going to do heating curves and cooling curves based on these equations only. We'll use these equations. And this one. One more thing. Remember we were discussing delta H naught units. It can be kilojoules per mole, but it can be kilojoules per gram. So delta H naught is equal to minus Q of the water over N. The unit is kilojoules per mole. But if you take minus Q of the water over M, M is the mass of the substance, then it will be kilojoules per gram. So you have to be very careful what unit they have given you in the exam. What are they asking? So take care of the units. Accordingly, you can change your equation. Is it clear? So moving on now on the new topic, heating and cooling curves. Okay, heating means temperature going up. This is heating. So when we are heating, heat is added. When the temperature is going up, it means heat is added. It's an endothermic process. But if I draw this graph like this, now what is this? What is this? High temperature to low temperature. What is it? Cooling curve. Cooling, right? Then this heat is added or released? This one. This is added or released? It's released, right? So we are going to discuss heating and cooling curves. They're exactly same, only in one thing, heat is in one curve, heat is getting released and you are calculating it. In another case, it is getting added, endothermic. Temperature is going up. Before we start this heating and cooling curve, you know that when we start heating something like solid, it will reach a point. Okay, Sushant, I'll check that. It will reach a point where it will start melting. Sushant is telling me something about quiz. So solid will become liquid. Where? At the melting point. Now understand this phenomena. Melting or freezing. It's the same thing. Melting and freezing is the point, is the temperature at which the solid is converted into liquid, and liquid is also getting converted into solid. They are in equilibrium. It's an equilibrium process, which is unit 7. We are going to start it today. Equilibrium. So this equilibrium is taking place whenever there is a phase change. So all phase changes are represented by equilibrium. During this change, the solid has very strong attractive forces. Liquid has less stronger. They are slightly loose. They are free. They can move. Solid cannot move, right? You know this. IMF is very strong, weak. So when solid is converted into liquid, at that time heat is needed to break the IMF. That heat is not showing you any rise in temperature. Heat is doing work. And what is the work the heat doing? It is breaking attractions. Breaking attractions. To convert the phase, to change the phase. Breaking attractions. And when it is breaking attractions, at that time, no rise in temperature. No rise in temperature means delta T is 0. You can see in this graph, there is a flat line here. That flat line indicates that you have added heat. You are adding heat. See here. You added this much amount of heat. This much amount of heat you added. But there is no rise in temperature. Check this flat line. You added this much amount of heat. Heat added. This much. But there is no rise in temperature. So what these lines are indicating in your this heating and cooling curve? Phase changes. These are phase changes. If I'm starting with solid, then what is happening at 20 degrees Celsius? Yes, melting. What is happening at 120 degrees Celsius? Boiling, right? So melting point and boiling point will not show you any change in temperature because at that time, all the heat, we are supplying heat. You can see this heat. And this heat has a special name. For melting, we call it as delta H of fusion. For boiling, we call it as delta H of vaporization. So when the boiling is taking place, liquid and gas are in equilibrium, right? Yes, Shrihan, boiling is the form of vaporization. So you can see here the heating and cooling curves will indicate the phase changes and when there is a rise in temperature. Now these lines, they indicate rise in temperature. Before we start doing questions, I'm going to ask many questions from you. Very first question is, can you see the difference in the amount of heat needed to boil or vaporize, to convert liquid to gas, and amount of heat to convert solid to liquid? And this is a general trend. This is in every heating and cooling curve, that delta H of fusion is always less than delta H of vaporization. For all substances, C part, answer this. Read this question. This is a very popular question. Who is going to explain why? Solid particles are tightly packed. IMFs are very strong. Liquid particles are slightly loosened, slightly. Liquid gases, they are far away from each other. No attraction, no repulsion, negligible attractions. So, going from solid to liquid, less amount of heat is needed. Solid to liquid, less amount of heat is needed. Why? Because we are just making them slightly weaker. IMFs are still there. IMFs are just slightly weaker, but they are there, slightly weaker. So less heat is needed. But as I go from liquid to gas, liquid to gas, IMFs are totally, we have to overcome them totally. IMFs, they become totally negligible, negligible. The change is big here. You have to overcome all IMFs. Overcome all IMFs. You need a large amount of energy to break all the IMFs in the liquid. Here, you are just making them slightly weaker. You are not overcoming them. You're making them slightly loose, weaker. You're separating them slightly. So less heat is needed. Are we clear about phase changes, melting, freezing, boiling? Are we clear about it? And how to identify them in the phase diagram? Sorry, this heating and cooling curves, not phase diagram. And why delta H of fusion is always less than delta H of vaporization. Okay, solid to liquid. What is this process called as? Delta H of fusion. The heat needed to melt them. And liquid to gas, solid, what is it called as? Delta H of freezing. For a substance, delta H of fusion, which is endothermic, positive, is always equal to delta H of freezing in magnitude. Only thing, one is endothermic, other is exothermic. Fusion is endo, you are breaking attraction, solid to liquid. Freezing is exo, attractions are made. Then liquid to gas is called as delta H of vaporization. Delta H of vaporization, liquid to gas. And gas to liquid is called as, anyone? delta H of condensation. And again, delta H of vaporization is equal to delta H of condensation magnitude for a particular substance. Magnitude is same. Only thing, one is endo, other is exo. In one case, you are breaking attraction, liquid to gas, attractions are broken. Gas to liquid, attractions are made. Then we need to know one more process, and that process is solid to gas. What is it called as? Solid to gas? Sublimation. Yes, sublimation. Delta H of sublimation. Is it endo, exo? Is it heat needed or heat released? Needed is positive. And what is this gas to liquid? What is it called as? Gas to liquid. This one. Delta H of deposition. Deposition. And again, the magnitude of sublimation and deposition is exactly same. Magnitude. Deposition is equal to condensation. But, oh, sorry, not condensation, sublimation. But one is endothermic, other one is exothermic. Deposition is exothermic. Deposition is gas to solid. Sublimation is solid to gas. And this is endothermic. Another important thing here that you can answer me. Just look at this diagram, this one, the one which I have made here. Can I use Hess's law here? Solid to gas, delta H of sublimation, that is solid to gas. You can go from solid to liquid and then liquid to gas is equal to, anyone? Use Hess's law. Solid to gas sublimation is equal to delta H of fusion plus delta H of vaporization. So please write down this equation because for fusion is solid to liquid, vaporization is liquid to gas. If I add these two equations, liquid liquid cancelled, I will get solid to gas. This is your delta H of fusion. This is delta H of vaporization. This is delta H of sublimation. Hess's law. I'm adding equation. These two will be added. So delta H of sublimation is delta H of fusion plus delta H of vaporization. So remember this equation. It will be given to you in the exam. If there is a question based on it, equation will be given to you. Or they may give you some information so that you can derive this equation. Right? Okay, ready for questions now? Read this question 96 here. You can see two flat lines, 1, 2. So what is the state of matter over here? Over here. What is the state of matter? Yeah, solid. And as what is happening? Temperature is increasing. What is the state on this red line? Let's say this is A point, this is B point. What is the state between A and B? A and B, A and B is solid only. State is not changing. B is also solid. But if somebody asks you what is the state here, B to C, this C, between B and C, between, so A to B is solid. B is also solid. Melting has not started. But between B to C, what is it? It's melting, right? So is it totally liquid? No, it is solid plus liquid. It's not totally liquid. It's solid plus liquid. You see this equilibrium I was explaining? Both of them are there. Solid and liquid, both of them are there. Solid and liquid, right? Bonds are breaking. What do you, Dhruv? Bonds are breaking or IMFs are breaking? And again, this is an AP question. When a substance is undergoing fusion, sublimation, physical change, IMFs are breaking, not the chemical bonds. Okay, so don't write bonds. You will lose marks because they are checking for it. So, what are we breaking? IMFs, intermolecular forces of attraction. You cannot break chemical bonds during it's a physical change, solid, liquid, gas. What is the state at C? At this point, C. What is the state at this point? It's only liquid. Only liquid. And what is the state between C and D? Between C and D. What is the state from C to D? At C and up to D. What is the state? Again liquid, right? What is the state at D? Again liquid. That boiling has not started. Between D to E, between these 2 points, what is the state? D to E. Both. Yes, Dhruv. Very good. D to E is solid. Oh, sorry. There is no solid, right? Liquid and gas. Between liquid and gas. Between D to E. Right on the top. Between. Not at D. Not at E. D is totally liquid. What is E? E. E is totally gas. This E, gas. And E to F? E to F is gas. Can you identify the states now? This is a question. They ask this question. They will give you, okay, what is the state of matter at D? Liquid. So I'm asking question. Everything is written here. I'm going to put a point and you have to answer the question. What is the state of matter here at this point? State of matter. Liquid and gas. Yes, both of them. Why there is no change in temperature at this line? There is no change in temperature. See, temperature is constant. Why? Yes. So this line represents a phase change. This line represents delta H of vaporization. So all the heat is used up in breaking IMFs and it is not visible to us as temperature. The heat is doing work here. And when we are doing work, then it is not visible to us as temperature. So there is no rise in temperature. Okay. What is the state of matter here? Yes, Sarayu, start answering. What is the state of matter here? What's the state of matter here? Here? Okay. So I think you have understood this. Can you answer A point? A question. Shrihan, can you check your answer? First, 0 is for water, it's not for every substance. Check your answer. Where the melting is taking place, melting or freezing, at this temperature. So answer is 20 degrees Celsius. Where the boiling, what is the boiling point of the liquid? Boiling point of the liquid, where the boiling has started. Yes. You know, melting point, boiling point, specific heat capacities, they are unique for a unique substance. They are used to identify the substance. So, do you think this substance is water? Is this substance water? Yes or no? No. Why? Because water has a melting point of 0 degrees Celsius and boiling point of 100 degrees Celsius. So, this must be something else, some other substance, right? Okay. Srayu, your answers? Start giving answers, Sarayu. So I'm going to clear this. Ready for next question? A substance X has the following information. Draw a heating curve starting from minus 50. For making the heating curve, we'll make the coordinates. And what is here on this coordinate over here? What is here? Yes, temperature. And what is here on this side? It's a heating curve. So heat added. Heat added. Now, can you explain what is happening? From where I have to start? Minus 50. Start from minus 50 degrees Celsius. They said this, starting at minus 50. Now, what's the boiling point, melting point? Is written here. So, let's mark these points. These are the temperatures, important temperatures. So I'm marking them. Minus 50 here, 50 degrees Celsius. This one is minus 15 degrees Celsius. Then let's say this is 75, right? Degrees Celsius. And up to what temperature they're asking us to make? Okay, they didn't mention anything. So let's start with minus 50. So minus 50 to 15, there will be a rise in temperature, right? Like this. And then it will become flat like this because this is the melting. Melting has started. So whatever heat I'm giving, that's not showing me any rise in temperature. And then after that, minus 15 to, yes, through minus 15 to 75, right? And this is again a rise in temperature. And then what happens after that? Starts boiling. This is the boiling point. So it will become flat. How much flat is going to become? Big, bigger than this, bigger than this, 3, 4 times more than this one. And after that, again, the graph will go like this. Let's say this final temperature is 100. Let's say 100 degrees Celsius. Now, the total amount of heat needed to go from minus 50 to 100 is the sum of all these steps. No, we are not going to do. Right now, I will ask you to measure. In the graphs, we are just sketching. Sketching means just make it, just to show that how it is going. Not exact measurements we are not doing. We are good with this? Okay. Now to calculate the total heat needed. Total heat needed. Needed. This question I'm making from my side. From minus 50 degrees Celsius to 100 degrees Celsius. How much total heat needed? I will add all these heats. Check here. So I'm using different colors to indicate different types of heat, like this line, this one. This is one type of heat. This is just raising the temperature of the solid. Then this one is doing melting, phase change, this one. Then this one is just raising the temperature of the liquid. The state is liquid here, right? It's just raising the temperature of the liquid. So I have to use different equation to calculate them. Then this one is boiling, right? This is boiling. The heat needed for boiling, right? This is the heat needed for boiling. Then next, this one is heat needed to raise the temperature of the gas. Gas. The state is gas here. Okay, I'm going to call them as Q1, Q2, Q3, Q4, Q5. So now the total amount of heat needed is Q1 plus Q2 plus Q3 plus Q4 plus Q5. I need to know these values. I can calculate. Look at the Q1. What is the state of the matter here? At Q1, what is the state? Solid. And there is a rise in temperature. Calculate Q1. MC delta T for solid. What is the M given? Let's say M given to us is 10 grams. 10 gram. So, how much Q1? 10. Specific heat capacity of the solid is given. See here, 3.0. 3.0. How much is delta T, children? How much is delta T? Delta T is from minus 15 to minus 50 to minus 15. Yes, 35. Yes, and get the answer. This is in joules, right? Okay, Dhruv is giving us, is it in kilojoules, Dhruv? See, you are using joules. Either you convert it into kilojoules. Shrihar, Dhruv, when you are using joules in specific heat capacity, your answer is in joules. 1050 joules. And not per mole. It's not per mole, right? It's Q. It's not delta H, it's Q. So 1050 joules. So this is 1050 joules, which I can write in kilojoules as 1.050 kilojoules. I can write like this much up to this red point. How to calculate This particular Q2, this one, this one. How to calculate this? Q2. I'm writing here. For Q2, I think I should use this space for writing. For Q2, is there any rise in temperature? No. Can I use MC delta T? No, delta T is 0. So what I'm going to use? I'm going to use this equation. M times delta H of N times, sorry, not M, because this value is given in kilojoules per mole. Kilojoules per mole. N times delta H. If I say the molar mass of the compound is 100 grams, can you tell me how many moles are there? You remember this equation? Delta H of the reaction is Q over N. This time this is not a cup calorimeter or bomb calorimeter, it's just a solid. So Q reaction over N. So from here I'm getting how much heat needed. N times delta H react. And what is delta H here, children? What is the name of this delta H? Back to the graph. What is the name of this delta H? Is it vaporization or fusion? It's fusion. So now you can calculate N. How much is N? Is 10 divided by 100. That is zero point 0.1. Okay, Shriyan, how come you are getting 5? Yes, Sanjana, good. What about rest of the students? Ashita, you're there? Not answering, but Srayu is not answering. Siri, start answering. 10 gram is the mass given to you. Molar mass of the compound is 100 grams. So moles are mass divided by molar mass. We know this equation. Unit 1. Mass divided by molar mass is the number of moles. That's how. Right? Okay. So now I'm calculating Q2, this one, which is called as delta H of fusion. So it is N, which is 0.1 times delta H of fusion, which is given here, 5.0 is 5.0 per mole. And this is kilojoules, so I'll get Q2 in kilojoules. So it is 0.5 kilojoules. So this one is, this heat is Q2, which is 0.5 kilojoules. Agreed? Now how to calculate the next? This one. How to calculate this, which is Q3? So what is Q3? There is a change in temperature. So which equation I'm going to use for Q3? There is a change in temperature, you can see. It's totally liquid. Which equation? MC delta T. Because there is a change in temperature. So use this equation. When there is no change in temperature, you cannot use it because delta T is 0. So Q2, I have to use fusion equation. This is fusion. Q3, I will use MC delta T. What is M here? 10. What is C? C of the liquid. This 2.5. What is delta T? From minus 15 to 75. How much is that? Delta T. This thing. Minus 15 to 75. How much is this? Saranya, minus 75 is the final temperature and initial temperature is minus 15. So Saranya is right and we all are wrong. Can you see Saranya has given the answer 90? It's 90. You start from minus 15 to 0, 15. And then 15 to 75, 75, 0 to 75, 75, 75 plus 15 is 90. This is T final and this is T initial and there is a minus here and there is a minus in front of 15 also. So when you take care of the sign is 90. If you don't take care of the sign, you will not get the right answer. So here the temperature is 90. How much in joules and then in kilojoules? Calculate it. 2250 joules, which I can convert in kilojoules, 2.250 kilojoules. So I'm writing here, this is 2.250 kilojoules. This one, 0.5 kilojoules. This one, 1.050 kilojoules. Who is going to help me in this? Q4. Give me the equation for Q4. Mhm. Q4 is vaporization. There is no rise in temperature. So I will use the equation N times delta H of vaporization. This equation. And what is N here? N is, we calculated earlier, 0.1. Delta H of vaporization is given to us 20. Can you see it's 4 times more than that of fusion, 20. And it is 2.0. So this value is 2.0. It's 4 times more than that of Q2, kilojoules. This is 4.0. Oh, sorry, 2.0 kilojoules. Calculate this now, this one, Q5. Now, which equation you are going to use for Q5? MC delta T. What is M? Given 10 grams. C for the gas, this is C, 1.0. Delta T, Dhruv is giving us delta T also. Delta T is 75 to 100, that is 25. Very good, Dhruv. And this answer is 250 joules. But we are working with kilojoules with the rest of the answers. So let's convert this into kilojoules. And in kilojoules, the answer is 0.250 kilojoules. Right? If you see, everything is given here in two significant figures. So all these energies I have to take in two sig fig, all of them. So Q1 is 10, okay, 1.1 kilojoules. This is Q1. Q2, 0.50, 2 sig fig. Q3, 2.3 kilojoules. Q4, 2.0. Q5, 0.25. Add them, add all of them, and that will be Q total, the total amount of heat needed going from here to here. Children, are we clear about this curve and how to use it to calculate the total amount of heat? Answer will be in kilojoules. Take care, you have to express your answer up to 1 decimal place. express your answer up to 1 decimal place, right? Because this number has only 1 decimal place. Here you are doing addition, subtraction. This number also has 1 decimal place. Addition, subtraction, the sigfic rule says that answer should be in minimum decimal places. So you are ready for such one more question? So remember, they can give you in the exam anything. Like I started from -50 and I reached up to 100. I calculated all the 5 energies. Q1, Q2, Q3, Q4, Q5. But they can say calculate from here to here, only Q3, or here to here, Q3 and Q4. So they can mark any points on the heating curve. They can give you any temperatures and they will ask you to calculate. You need not to be such big lengthy question. But this lengthy question has covered everything. Ready for one more? I'm going to erase this now. Shrihan, is it okay? Sarayu, now your turn, okay? Sarayu, Ashita, please answer here. Read this question. Make the heating curve. We are going to make the heating curve. All of you are reading the question? Reading the question is an art. So, what is here on this coordinate? And what is here on this coordinate? Mhm. On this one, what should I take? This is your y-axis, right? So, what should I take on y-axis? What should I take on x-axis? If you don't know the coordinates, then how you're going to start the question? Shrihan, Dhruv, what are the coordinates here? Very good. Sarayu, yes. Read, speak, write. Here is the temperature. And here is the heat added. It's a heating curve. It's endothermic added. Mark the important temperature points. Important temperature points. Is ice. Do you know the melting point of ice? So one temperature is this, which they have mentioned here, -20 degrees Celsius. Another important temperature is melting point of ice, 0 degrees Celsius. Another important temperature is boiling point, 100 degrees Celsius. They are not mentioning it. You should know it. You drink water every day. You should know everything about water. Its specific heat capacity, its density, its melting point, its boiling point. That we should know. It is the most abundant compound on the earth. Okay. And what is the other important temperature mentioned? 250. So I have to start from -20 and reach up to 250. That's what they are saying. Total mass of the ice given to me 0.500 kilogram means 500 grams. Right? So ready? So what should be the lowest temperature here? What temperature should I take here? This one? -20. Starting temperature. -20. Right? Siri. And then mark 0 degree. Then mark 100 degree. Then mark 250, right? So this can be some estimated values. You need not to be very accurate. Now, minus 20 to 0. What will happen? Because this is the melting point. Minus 20 to 0, the graph will go up. There is a rise in temperature. This is the Q1, the amount of heat needed to raise the temperature from minus 20 to 0. What happens at 0? It will become flat. And this is Q2. Then after that, what happens? Up to 100, it will go up. Temperature is going up. And this is Q3. This is heat needed. Then at this temperature, it is Q3. Then at boiling, this is boiling point. What happens at boiling point? Like this. This is Q4. This one. This is boiling. And then up to 250. This is Q5. Ready, children, to answer all the question? Give me the equation to calculate Q1. Q1. This. MC delta T. Is M given to us? Plug in the values. Everything is given. Q1 is solid, ice. What is M? 500 grams. 500. What is C? C of the ice. Take the C of the ice. Is given. 2.03. What is delta T? Yes, children, delta T. What is it? Sarayu, what is delta T? Is 20. The answer will be in joules. Okay, calculate. Get the answer. And then let's work on Q2 also. Q2, there is no rise in temperature. It's fusion, melting. So what is Q2? Okay, this answer you are giving me in joules. Can I convert this in kilojoules? It will be easier to write. Up to, we'll go for two significant figures. So in kilojoules, it will be 20. Yeah, there is a decimal here. Q2. Q2 is N times delta H of fusion of water. But do I know N? Yes. I can work out N. N is the mass of water, which is 500 grams ice, divided by the molar mass of ice or water. They have the same formula, is 18. How much is N? Plug in that value of N here. It's 27.8. And what is delta H of fusion? That is given. Delta H of fusion is given to us 6.02 kilojoules. This is in kilojoules. That is the reason I said let's convert all of them in kilojoules. So we converted this in kilojoules, but this is already in kilojoules. And how much is this? $167.2 kilojoules. We'll take care of the sig fig later on after that. Q3. Here also you can take care of sig fig. in the last. Q3. Q3 is this. What equation should I use for Q3? MC delta. What is M? 500. What is C? This is liquid, right? This one is liquid. Liquid water. What is C? 4.2. Here they have given 4.2. What is delta T? Delta T, children? Very good, Sarayu. What is delta T? Ashita, delta T? Yes, 100. And answer will be in joules because this is 4.2 joules. Convert that into kilojoules and what's the answer? Can we convert this into kilojoules? Okay, 210 kilojoules. Is it 210 or 21? I think you were showing me 40, so 210 kilojoules. Okay, that is Q3. Calculate Q4 now. Q4. Which equation you are going to use for Q4? And delta H of, yes, Dhruv. And delta H of what? Vaporization. Very good, Dhruv. And N is, and we call calculate it. This one. This is N. 27.8. And delta H of vaporization is given in the question 40.7. Can you see it's very large as compared to fusion? Kilojoules. How much is this? Are you sure that these answers are right? 210. Yeah. M is 500 gram. Okay. Very big amount. 1131.46 kilojoules. Sarayu, because delta H of vaporization is in kilojoules. If you're multiplying, this answer will be in kilojoules. Calculate Q5. Q5 here. What equation we are going to use for Q5? It's a gas. There is a change in temperature. MC delta T. How much is M? 500 grams. Same. What is C? C of the steam. Steam means vapors. Vapors of water. So 2.0 delta T. Delta T is, this is 100. This is 250. So 100 minus 250 minus 100. 150. Delta T is 150. And answer will be in joules. So convert this into kilojoules, divide by 1000. Then it will be in kilojoules. - 150 kilojoules. Very good. Now, what is the quantity of heat needed to raise the temperature of half kg of ice from -20 to 250? You are going to add all these values. The amount of heat needed will be Q total will be Q1 plus Q2 plus Q3 plus Q4 plus Q5. That's the total amount of heat. And we calculated all the heats. You can add them. I'm highlighting the values which you have to add. This is Q1, Q2, Q3, Q4, Q5. Add all of them and you get the Q total. Yes. And we have not taken care of sig fig. I think all the answers will come in two significant figures. So this should be into, this should be into, this should be into. Then you have to apply the decimal rule. So I think you can express this answer in, because when I express the answer in two sig fig, all of them, then after decimal, there is no number. So we can put the answer in minimum decimal places, and that is 1679 kilojoules. I use the addition subtraction sig fig rule. So work out on this on your own. Check whether this is the right answer in significant figures. So this question we have made very lengthy, starting from -20 to 250. But if let's say they are asking how much heat is needed going from this 0 degrees Celsius, solid ice is given to me at 0 degrees Celsius and then is converted into liquid at 100 degrees Celsius. How much heat? What's the answer then? Just Q2 plus Q3, correct? You're going to add Q2 and then you're going to add Q3. So from 0 to 100. But if they say that starting from 0 degrees Celsius, but not solid ice, liquid water, H2O liquid, then from where should I start? It's not solid, it's liquid. But temperature is this. From where I'll start? From here and go up to 100. So it means I need to calculate only Q3. That's it. So you have to be careful that what temperature and what state of matter they have given so that you can identify from where to start and where to end. This is equilibrium. This one is equilibrium. So that's a different type of question. They will not say that, or they may say that when the melting is taking place, how much heat is needed when the melting, they are going to tell you in terms of temperature. So at this equilibrium, the temperature is same. But if they say solid, then start from here. If they say liquid, then start from here. From here. If they say solid and liquid, then you can take anything in between. But for that, you're just going to use that delta H of fusor. I think you'll get the same answer what you are getting here. So they will not ask how much heat at this point, right? So we are okay with this concept. So making a heating curve here, just for practice. This is for water. We know all important temperatures of water. I'm starting from -5 degrees Celsius. So it means water is solid, ice. First, the temperature of the ice will go up and it will reach 0 degrees Celsius. Then it starts melting. Then again the temperature will start going up and it will reach 100. Then it starts boiling and then vapors. Okay, now marking them A, B, C, D, E, F. I'm marking the amount of heat needed for every step. This one is Q1, MC delta T, Q2, n times delta H of fusion, Q3, MC delta T, Q4, n times delta H of vaporization, Q5, right? So I'm going from A to F. Now the question is like this. There is liquid water at 100 degrees Celsius and you want to convert that into H2O gas at 150 degrees Celsius. This is, let's say, 150 temperature. So how much heat is needed? What are you going to calculate? Liquid water is where in this line? Is it at D or E? What is liquid? D. So you start from here. So it means for this, the answer is, what is the answer for this? Q4 plus Q5. That's it. You add this and this. This Q5 is MC delta T. Q4 is N times delta H of vaporization. You add these two values and you will get the answer of this question. But if they say, if the question is like this, liquid water at 0 degrees Celsius to steam at 100 degrees Celsius. How much heat? 0 is here. So to liquid water is B or C? Liquid water is B point or C point? Remember, B is solid. Between B and C, solid and liquid. C is liquid. So from where you will start? You start from here, right? And what is D? D is at 100. So final temperature they are saying 100. But what is D? Liquid or gas? D, liquid. So, but you need steam. Steam means gas. So where you should go? E. So what's the answer for this? How much heat? Q3 plus Q4. So these type of questions can be there in parts. They will ask you in parts. So they will give you states like this, conditions like this. And you have to identify from where I'm starting, from where I have to end, then how much heat, Q3, Q4 is the part here. You need to know this much amount of heat. Starting from here, this is heat, right? Heat added. So are we clear about it? Okay, children. So the heating and the cooling curves is the last topic. There are plenty of questions based on it. Now this question, I'm not going to do it. I'll explain you how to do it. Consider 75 grams of water at 125. So what is the state? Gas. 215 kilojoules of energy is removed. So is it a heating curve or cooling curve? You are coming from 125 and heat is removed. So when you remove the heat, what happens to temperature? It goes down. Mark the temperature. Important temperature, you are starting with 125 degrees Celsius. Next important is 100 degrees Celsius. Next important is 0 degrees Celsius. So as you start removing heat, what will happen? First, it will touch the boiling point. Now this time is called as condensation. And then it will become flat, right? Like this. This is minus Q. Heat removed, exothermic. Method is same, everything is same. Only thing that now is going to retain a negative sign. Then you come to 0, the freezing point. And then it starts freezing. This is freezing process. It's becoming ice and then down. The total amount of heat needed, heat removed is this. So what you are going to do? You'll calculate this Q1 by using MC delta T. You'll calculate this Q2 by using N times delta H of vaporization, which is also condensation now. This is condensation. Reverse process. You're going to calculate Q3, which is MC delta T. You're going to calculate Q4, which is N times delta H of freezing. Reverse process, cooling, cooling. And then Q5 MC delta T again. But what you do? Because they are saying what is the state of matter at 215 kilojoules of energy is removed. What phases are present? That's the question. Question is saying when you remove 215 kilojoules of heat, what is the state of matter? Is it solid plus liquid, or liquid plus gas? What is it? So what you are going to do? Check Q1, add Q2, Q1 add Q2. Check. Is it less than 215? If it is less, then add Q3. Is it less than 215? If it is yes, then add Q4. And after adding Q4, if this answer is greater than 215, then you stop. Q1 plus Q2 plus Q3 is less than 215. That you can check. You calculate this, this, this. Keep checking. This is less than 215, but this is more than 215. It means, where is your material? Here. It's not here. It's not here. It's here. Somewhere. Right? And what is the state of matter here? What is the state? Solid and liquid. It's a phase change. So when you remove 215 kilojoules of energy, you keep adding your Q1, Q2, Q3, keep comparing it with 215. Check where it is crossing the 215, where it is more than that. Stop there and identify that point. Think about that point. I said don't take this because you remember Q1, Q2, Q3 is less than 215. It means you are not here. You are not here. Where are you? Here. You added more amount. You are somewhere here, right? So this kind of question may come in a very simple way. So children, for my side, I'm giving you very complicated examples, complicated questions, lengthy questions. But when they come in the exam, they simplify them. So if you are not understanding, you let me know. I can split it into more simpler form. But have you understood this question? Yes or no? Cooling curve. So ready for the new unit? We are starting new unit. The new unit is chemical equilibrium. And children, in this unit, it's a very big unit, but it's very interesting and very simple. But the same thing will become very complicated if you don't follow, if you miss the class, if you join late, then you start missing the concepts. It's completely based on concept. And in fact, am I sharing something? No, not yet. You can see this? This unit is very important for your unit 8 and unit 9 also. This is the most important unit of chemistry and very simple, very interesting. So, ready? Do you remember that in unit 5, I left one topic? If you remember that topic, that was steady state approximation. What I'm sharing. Okay, now you can see the unit here, unit 7. So, one topic was left in unit 5, steady state approximation. I'll teach you now, not today. You have to remind me in the next class, steady state approximation. I left the unit at this particular topic because it is based on chemical equilibrium. So first we'll understand the equilibrium and then we'll go this topic again, we'll do it, steady state approximation in kinetics. Okay, now let's try to understand equilibrium. First of all, the equilibrium is, I'm taking you on the whiteboard to make you understand the meaning. Equilibrium is the state of system. You know the system, right? System surroundings. It is the state of system with lowest energy. If it is actually it is free energy, more accurately free energy. So lowest free energy. If it is with the lowest free energy, then we call the system is in the most stable form. Most stable form. That's the meaning of the equilibrium. And what nature wants? Nature wants stability, right? Nature is looking up for the stability. Nature is pushing everything, all the system in the direction of stability, right? Okay. If I represent this free energy as delta G, which you are going to learn in your unit 9. So any system which is with the lowest free energy, possible lowest free energy, is in equilibrium. Let's make it in the graphical form. System here is a reaction. Reactant to product. That's the system, right? Okay, let's say this is the energy of the reactant. This is delta G, the free energy. Now you should make yourself familiar with this delta G, which is called as Gibbs free energy. So if this is the reactant here, and let's say this is the energy of the product, let's say. This is also delta G. When this reactant is giving you the product and setting up an equilibrium, the energy will go like this. So what is the lowest point of this curve? Here. This is equilibrium. The system is in equilibrium at this point. This is equilibrium. Okay, let's mark it on the other way. The lowest energy point is the equilibrium. This point is equilibrium. And what is the amount of reactant here? This at equilibrium, right? If you see, the graph is more in the direction of the product or reactant. Can you check that? Can you see that the amount of reactant has decreased more? This one is more decreasing. So what is more at the time of equilibrium? The product is more. But the system is still in equilibrium. If I make it like this, you can say the product is more. But if I make it like this, check another curve. If I make it like this, then what is more at the time of equilibrium? Reactant is more. So equilibrium doesn't mean that products and reactants are equal. Equilibrium only indicates that it has the reactant and products are together with the lowest free energy. They are not equal. They may or may not be equal. So is the meaning of equilibrium clear? So nature pushes everything in the direction of equilibrium. You take a reactant, let's say you have taken N2O4. N2O4 has a tendency to undergo dissociation and it gives you NO2. So this is the container. In this container, there is only N2O4. Only N2O4. Nothing else. So this is the initial point. Initial. Initial means when the time is 0. So I started only with N2O4. After some time, you will see that there is some brown color. This is brown gas. After some time, you will see that the container, which was colorless, no color, now it has very light brown color. So brown color means that brown color is uniformly spread out on the complete container. It means this has started forming. After some more time, give more time. After some more time, you will see the intensity of the brown color in the container has increased. Please understand this. If you understand this, then equilibrium is not going to trouble you at all. The intensity of the brown color has increased. It has become dark brown. Means more NO2 is formed. You give more time, give more time, give more time, give more time. No change in the intensity of color. No change in the intensity of color. What does it mean? It means equilibrium has set up. It means now the system is in equilibrium. This is the initial when the time is 0. It was totally colorless. This is, let's say, after 10 seconds. there is some NO2. There is NO2 and there is N2O4. This is, let's say, after 20 seconds. There is more NO2, more NO2. Intensity has increased. But after 30, 40, 50, nothing changing. No change visibly, nothing is changing. Color intensity is same. So they say that when you cannot see anything, no change is visible, is called as equilibrium. This is not visible. The change is not visible. If I ask you to make the graph of this graphical representation, here children, this is time here, time. I started with 0 time, initial, initial, 0 time. What is there initially? Only N2O4. So let's say this is the concentration here and this is the concentration of N2O4. The reaction is that N2O4 breaking down to give NO2. NO2 is brown in color, N2O4 is colorless. So slowly you will see the intensity of the color is increasing. So initially N2O4. And what's the amount of NO2 initially? Initial amount of NO2 children in this container? Was there any NO2 initially? When the time is 0, when the reaction has not started? How much NO2? Anyone? I hope you're listening. How much NO2 initially? Ashita. In this container, how much NO2? None. Yes, 0. 0. Very good. Very good. So what happens as the reaction starts? As the reaction starts, what happens to the concentration of N2O4? It decreases. As the reaction starts, it decreases. What happens to the concentration of NO2? Yes, NO2 increases. Yes, very good. And you'll reach a point when there is no further change in the intensity of the color. It means these concentrations have become constant. You can see this? And this state, this one, is called as equilibrium. And what is there before that? What is this state called as? This one is called as initial. This one. Initial when the time is 0. 0. And what is this called as? In between the equilibrium and the initial, this part. Okay, I'm marking it. This one. Change. Change. You know, that's nature is going to push the system in the direction of equilibrium. Always. You need not to do anything. Like here, what are you doing? Nothing. You just picked up a container and you placed N2O4 in that and you left it untouched. Nature is doing it because nature wants minimum energy. So it is forcing this N2O4 to undergo decomposition, giving you NO2, and slowly the equilibrium is set up. Initial is not equilibrium. Change is not equilibrium. Change is happening. It is happening to get the equilibrium. So whatever change you can see here in the color, nature is forcing it so that equilibrium can be achieved, right? But once the intensity of the color is constant, it means the concentrations have become constant and that is called as equilibrium. Is it okay? So the reaction, whatever reaction is there, that reaction will undergo in three different parts. First, initial. You have to focus on the initial concentrations, what you added, how much you have added. That is called as initial when the time is 0. Then the system is struggling. This is struggling state, struggling. System is moving in the forward direction, reverse direction to get the equilibrium. This is struggling form, changing. And finally, the system is coming at peace with equilibrium. We call it as equilibrium constant K. It's a constant. You can see the concentrations are constant. This is K. But before that, all this area is not equilibrium. We call it as Q. Q is the reaction quotient. It represents a struggling state for getting the equilibrium. Q wants to become K. When this Q is equal to K, then we say the system is in equilibrium. And this K is called as equilibrium constant. Is the meaning of equilibrium clear, children? So equilibrium is the most stable form of the system with lowest free energy. Whatever you leave, whatever reactant you started, you left the reaction mixture, you are coming back after 10 days, 20 days, there is equilibrium. Nature will force every reaction in the direction of equilibrium because it is the lowest energy state. Now I'm showing you this on the presentation. Same example, right? And you can see here, we started with colorless, no color. You can see there is no color, no color. So this is N2O4. Can you see the brown color now? And the intensity of the brown color from here to here increased. But after that, what is the intensity of the brown color? Constant, not changing. So let's write down the number of molecules of N2O4 here and NO2. How many molecules of N2O4 in this picture? 1, 2, 3, 4, 5, 6. Is there any NO2? No. Can you calculate here, children? In the second container after some time? N2O4 is 2 nitrogen, 4 oxygen. This is N2O4. How many N2O4 now? Count it. Ashita, Sravya, can you count it? Oh, not Sravya. Sarayu. Sorry. How many? 4. Yes, Sanjana, good. And how many NO2s? Can you count the NO2s now? NO2s. NO2s are also 4 because equation is like this. N2O4 breaking down, 1 is breaking down to give you 2 NO2. So if it is 6 to 4, it means 2 has reacted. 2 will give you 4. Take care of this coefficient. 2 will give you 4. How many here? Count N2O4. Mhm. 1, 2, 3. So it means out of 6, 3 has reacted. So how many NO2s will form? 6. Here, check here. 1, 2, 3. How many NO2s? 6. Check here. 1, 2, 3. How many? 6. Is there any change in concentration here? No. This is called as equilibrium. The system is in equilibrium. Whatever you do, if you do some external changes, it will get disturbed, but it will restore itself. But otherwise, now the system is in equilibrium. And what is this? Non-equilibrium. This is initial. Initial. And from initial up to here is the change. And this is the equilibrium. You're going to learn Rice table. R reaction, I initial, this one, 6 and 0. Change, what's the change? 6 to 3. So minus 3 plus 6, that's the change. It has become from 0 to plus 6. Equilibrium, 6 minus 3, 3. 0 plus 6, 6. Can you see at the equilibrium, this is the state? So we are going to work plenty of things on the Rice table, which you can understand from the graph. Reaction, initial state, change is happening to get the equilibrium and the equilibrium. Are we clear about the equilibrium, children? Concept of equilibrium. So what happens at the time of equilibrium? There is no change in the concentration of the reactant or product. Read this line. So I'm showing you one system here. Here is the concentration. I'm talking about an equilibrium. A is in equilibrium with B. And this is how it's taking place. I'm placing some important points here. Okay. What is this called as when the time is 0? What is it called as, children? You remember initial, change, equilibrium. What is it? Initial. What does it mean? What is the meaning of this initial? That you are starting only with A. So what's the amount of B initially? Let's say you started with some amount of A, X. What is B? 0. That's the initial, right? Okay. Now what does this represent? This part? System wants to come in equilibrium. What is this part representing? Hmm. Yes, children. I was using that word earlier also. Remember Rice table. Reaction, initial, then anyone? What is it called as? Remember you were saying intermediate. I said no. I used the other word. Change. See, I'm teaching you. You're forgetting within minutes. So just understand it will be more difficult to retain or to recall things after a month. So please write down everyone. This represents change. All of you, please write on change. Hello, am I audible? Yeah, so I asked you to write down change. No one is writing. Change, type change. Dhruv, can you type change? Yeah, this part is representing change. And what is this part representing, children? This one? Here, this one. What is it representing? It is representing Unit 7, equilibrium. Unit 7. This is equilibrium. So it is reaction, initial, change, and then equilibrium. And this part we are going to learn as K. And the change part we are going to learn as, yes, any one of you? Remember, I told you. What is it? Yes, this Q is big. Okay. This Q is not that small Q. That small Q represents heat in Unit 6. This represents reaction quotient. What this Q wants? It wants to become K, right? Now the next thing, when system has achieved an equilibrium, then do you think the reaction has stopped? So at this point, when there is no further change in the concentration of A and B, this is your B, this is A, there is no change in the concentration of A and B with time. Here is time. So do you think reaction has stopped? No, reaction is still going on. Equilibrium is a dynamic state. It is the state at which the rate of the forward direction means A to B, this rate is equal to the rate of the reverse direction. Rate we have done in kinetics unit 7. If I say what is the rate of the forward direction here, forward, if I take it as elementary reaction, let's say this is elementary. What's the rate law for the forward direction, this direction? It is K1, or you can say K forward times concentration of A. This is the rate law for the forward direction. It is rate laws are always in terms of concentration of reactant. So I've taken reactant here. It's elementary. So this coefficient is the order also. Elementary steps. I'm talking about elementary step. What about B, the reverse direction, this one? Now B is the reactant. So rate law for the reverse direction, when B is the reactant, going in this direction, see, B to A is K. What is K here? It's not equilibrium constant, it's small k in fact. Do you remember what is K? In the rate law, what is K? Yes, children. Anyone doing unit 5? Dhruv, what is K? No, it's not equilibrium constant. It's the rate laws. Unit 5. In Unit 5, I didn't teach you equilibrium constant. In Unit 5, this K represents rate constant. Small k, you can take it like this. Rate constant. right? Okay, now at the time of equilibrium, the rate of the forward direction is equal to the rate of the reverse direction. Rate of forward is equal to rate reverse, means the reaction is going equally in both the direction. This is the situation at the time of equilibrium. The reaction is going equally with equal rates in both the directions. This is equilibrium state. This can be multiple choice question. What happens at the time of equilibrium? And they will give you all these options. Then you have to pick up this one. What is the rate of the forward? This. So K, the rate constant for the forward direction, concentration of A, is equal, reverse is this. K, the rate constant for the reverse direction, concentration of B. Now these two are equal. I'm going to isolate the constants. There are two constants you can see. Isolate them. K, the rate constant for the forward direction, divided by rate constant for the reverse direction is the concentration of the product B, this for this reaction, B over concentration of A. And this is called as this one. This is called as equilibrium constant. Multiple choice question. So what is K, children? K is an equilibrium constant, capital K, but it is the ratio of the rate constant for the forward direction to that of reverse direction. And we do have expressions for K. Like for this reaction, A to B, my equilibrium constant for this one is the concentration of this B over concentration of its reactant A. Are you understanding this? So equilibriums are dynamics. Equilibriums are dynamic. Dynamic means the system has not stopped. The reaction has not stopped. So what is happening? Whatever amount of A is converted into B, whatever amount of A converted to B, exactly same amount of B is converted into A. Like for example, there is a shop. Let's say there is a kind of bakery shop and it has some display items here. Bread, cakes, biscuits, all these are displayed here. Whenever you enter in the shop, you see that there is no change. Bread is still there, cake is still there, biscuits are still there, exactly in the same manner. Why? Is the sale not going on? Is the shop is customers are not coming in the shop? Yes, they are coming. Sale is still on. But if let's say this one bread goes out of this counter, what the shopkeeper doing? He's placing another bread. So the rate of sale means the bread moving out and the rate of replacement of the bread is same. That's why you cannot see any change. But it does not mean that the shop is not working. It does not mean that the shopkeeper is not earning money. Things are happening there. But for your eyes, you always feel, oh, whenever I come, this bread is lying here only. It's a different bread now, right? Same is here. Equilibrium, when you look at the equilibrium state, you'll feel that nothing is happening. Nothing is happening. But things are happening. And the rate of the forward direction is rate of reverse direction. If one A is converted to B, at the same time, one B is converted into A, so that this ratio B to A, which I'm calling it as K, the equilibrium constant, is a constant value. It will not change. The value will be constant. That's the meaning of dynamic, children. So they may ask you the meaning of dynamic state of equilibrium. Dynamic means reaction is still going on, but at equal rates, right? The system is not static. Static means fixed, nothing happening. I hope all of you are listening this because I'm going to ask questions now. Are we clear about K? Any questions, children? No questions? Okay. So we are left with few minutes. So before ending the class, I want you to learn how to write down K expression. So I'm giving you one general equation. There is a reaction. So please pay attention now because I'm going to ask questions. BB in equilibrium with CC and DT. The equilibrium constant K for this reaction is the product of the concentration of products. Products are C and D. So concentration of C raised to power is coefficient, this coefficient in the balanced equation, times concentration of D raised to power is coefficient divided by concentration of A, the reactant, raised to power is coefficient, concentration of B raised to power. Concentrations. Do you know concentrations are measured in? What's the unit of concentrations? When I put in square bracket like this, what is it called as? Yes, Lasya? Very good. Ashita, molarity. So remember, equilibrium constants are in molarity when you are taking Kc. Please do not work with moles or grams. If you are working with moles and grams, your answer will be wrong because K is in terms of molarity. And everybody knows molarity. Molarity is moles per liter. So you are going to work with moles per liter. And another important thing about K, no units. No units. Now I'm asking one question. You can answer the question and you can leave the class, but not without answering. All of you have to answer. Okay? Reaction is this. Nitrogen gas reacting with hydrogen gas, manufacturing ammonia gas, and there is an equilibrium. What is Kc expression for this reaction? I've already explained you how to write. So you type your answer here. You can leave the class, but if you have some questions, more questions, you can stay back. Very good, Dhruv. You can leave the class if you want. Perfect. Bye. Shrihan. Perfect. Do not leave the class without answering, please. Ashita, okay, good. You're leaving class without answering? Few of you. Ashita, good. Good, Sri. Bye. Bye, Sri. Lasya, where's your answer? Sanjana, good. Perfect, dear. Lasya, good. Srayu, bye. Good.